And number 3, we have a table of values here that gives us time. And our CFT function is in ounces. It's hot water dripping through a coffee maker, filling a large cup of coffee. The amount of coffee in the cup at time t is given. It's a differentiable function, it says. T is measured in minutes. Selected values are given in the table above. And our job here in part A is to use the data in the table to approximate C of C prime at 3.5. So again, we've seen this problem quite a few times at this point. We have data for 3 and 4, so the slope estimate at 3.5, we can just find the slope between those 2 points, and that will give us an estimate for what's going on at 3.5. So if we do 12.8 minus 11.2, 4 minus 3, turns out to be 0.4 over 1, which is 0.4, of course. So 0.4 would be our estimate for the slope. Nope, I lied, 1.6. I'm doing that backwards in my head, sorry. So 1.6, that is. And units on that are going to be ounces on top, minutes on the bottom, so ounces per minute. So it says using correct units, they gave us a point for getting the 1.6. They also gave a point for having ounces per minute. So 2 points total. Okay. The next part says, is there a time between 2 and 4 at which the derivative equals 2? Sounds like a mean value theorem problem since we have the 2 endpoints given and we have a derivative somewhere in between. Okay, so is there a time? So let's calculate. If I do 2 is 8.8 and 4 is 11 or 12.8 still. Okay, so if we do the subtraction, find the slope between the endpoints here, we would get 4 on top, 2 on the bottom, which gives us 2. So we would say yes, since the slope between the endpoints is 2. Okay. F prime, not F prime, but C prime, I should say. C prime of t equals 2, somewhere on that 2 to 4 interval. Okay. And because of why? Because of the mean value theorem. Okay. So they gave 2 points for that if you calculated the slope of the endpoints. Okay, you got a point, as you can see here. And then if you said yes because of the mean value theorem, you got the other point. So 2 points total there. Where the mean value theorem tells us that somewhere on the interval, as long as we have a continuous and differentiable function, somewhere on the interval, the slope between the endpoints is equal to the slope of the curve. In other words, the derivative equals the slope between the endpoints at least 1 point. The intermediate value theorem tells us that if we have a continuous function, okay, and we go from, say, a value of 2, -6 to 3, 5, okay, then we would have had to cross the x-axis there. That we're gonna get all the intermediate values between the y value -6 and the y value 5. Okay. Okay. Then the next part says use a midpoint Riemann sum with 3 subintervals to estimate the 1 through 6 or 1/6 of 0 to 6 of CFT. So looking at our intervals, we go from, our intervals would be from 0 to 2, then 2 to 4, then 4 to 6. So we do have uniform subintervals this time. So they would be of length 2. We're going to calculate it at the midpoints, which are going to be the odd values here, 5.3, 11.2, and 13.8. Okay. So that right there would calculate the area under the curve. And of course, we're going to take that and we're going to multiply it by 1/6. Okay, if we do all that, it turns out to be 1/6 times 60.6, which would give us 10.1. The units on here were ounces times minutes, but then we divided it by 6, which is minutes. So ultimately it's ounces. And what would we say that is? That's the average value of CFT on 0 to 6. Okay. So it's just the average value. Okay. Okay. And if you wanted to say it in the context of the coffee pot, you could say it's the average number of ounces that are in the coffee pot at any given time on that time frame. Okay. So average amount of coffee in the cup, if you will. They gave 3 points if you did the midpoint sum. You got a point. If you got the right approximation, which is 10.1, you got 1. And then if you discuss the fact that it's the average value of the C function, okay, you got the 3rd point. Part B was 2. 1 for calculating the slope and then one for talking about the mean value theorem and the fact that it's a yes. Alright, then finally in part D it says the amount of coffee in the cup is modeled by this B of t function, and it says using this model find the rate at which the amount of coffee in the cup is changing when t equals 5. So our B of t function, 16 minus 16 e to the negative 0.4t, and this is the amount function for coffee in the cup. We want to know what's the rate of change at time 5. So it would be nice if this were a calculator problem, but it's not. If it was a calculator problem, then we could just use our ender command again. But the derivative of this is going to be, keep in mind that the e function, its derivative is itself times the derivative of the argument. So we're going to have e to the negative 0.4t, okay, times the derivative of e to the negative 4t, which is times negative 0.4. And we still have the negative 16 out in front because it's a constant multiple. And so if we multiply this all together, negative 16 times negative 0.4, going to be 6.4 e to the negative 0.4t. 16 times 4 is going to be 64, but it's 0.4, so I'll make it 6.4. And then we want to know the value of this at time 5, so we have 6.4 e to the negative 0.4 times 5. So it'll be 6.4 e to the negative 0.2. Okay. All right. And keep in mind that it's a non-calculator problem, so do you expect to have this memorized what the decimal for e to the negative 0.2 is? No, so just leave it like that. That's it. Okay, and the units here would be in ounces per minute. All right. You could have 66.4 over e to the negative, or e to the positive 0.2. If you did it like that, that's fine. Oh, yeah, absolutely. Yeah. Yep. Yep. Definitely. Yeah. If you just change that to 4/10 or 2/5 and then multiply it, you'd have 32/5. That's totally fine. Okay. Points awarded for that. They gave you 2 points. If you found the derivative correctly, they gave you a point. And if you found the value, they gave you the other point. All right. Then let's check out number 4 next. We have a function that has a bunch of different areas on it. Tells us that this is the graph of the derivative of f. Tells us that the derivative is a twice differentiable function of f on the closed interval 0 to 8. The graph of f prime has horizontal tangents at 1, 3, and 5 as it appears on the graph. It's correct. And they give us the areas of the regions as labeled. And they also tell us that the function f is defined for all real numbers, satisfies also 8, 4, so they give us an initial condition for f. And so we need to, in part A, find all the values on x on the open interval 0 to 8, so not including endpoints, for which f has a local minimum, and justify your answer. So we know that f would have a local minimum when the derivative is equal to 0, and also the derivative changes from negative to positive. Okay. So there the derivative equals 0. But the derivative on the left and the right are both positive, so this would not represent a minimum. Okay. The other points are going to be where we have this one right here would be 4, and we can see here though that the derivative changes from positive to negative, so that would actually indicate f having a maximum. And then finally, right here would be 6. That's where a derivative changes from positive to negative, negative to positive. Okay, which would indicate a minimum point. So we would say that at time 6, okay, or x equals 6, I should say, we have a minimum point because that's where the derivative changes from negative to positive. So just 1 point there if you found that and told why. Okay. And again, it's as simple as that. The derivative changes from negative to positive, so therefore at 6 we have a minimum. Okay, 1 point for that. Part B says determine the absolute minimum value of f on the closed interval 0 to 8. So as soon as I see that closed interval, I'm going to make a candidate test problem out of it. So f at 8 we know is 4. They told us that information. Okay. All right, and then we need to figure out what is f at 0. Okay. So f at 0, okay, we know that they don't give us the information about what f at 0 is like. True? Okay. All right. But we know that with this function, as we go from 0 to 1, we're accumulating an area of 2, okay, then 6, then we subtract an area of 3, and then finally we'd add an area of 7 to get to the value 8, 4. True? So let's work backwards from that information and see if we can figure out what 0 is. So let's start with 6. Okay, at 6, if I'm at 6 and I add 7 to get to 4, wouldn't then 6 have to be negative 3 for a value? True? And then if I were to go from 6 back to 4, okay, my 4 here would be, I would have to add 3 to, or excuse me, subtract 3 to get to this, so wouldn't 4 or 0 be the point on F? Because again, if I'm at 0 here and I add a negative 3, then I'm going to be at that value of negative 3. Similarly, as I go back to 1, okay, I'm going to have added 6 to get to 0, so therefore I'm going to have negative 6 here. And then finally at 0, I'm going to have added 2, so therefore my answer here for 0 is negative 8. So think about that going forward again. Okay, if I start at 0, negative 8, and I add 2, I'd get to negative 6. And then I'm going to add 6 and get to 0. Then I'm going to subtract 3 and get to negative 3. Then I'm going to add 7, and I'm going to finally be at y equals 4 for this function. So those are all my candidates. Those are all the places where we're either an endpoint or where the derivative equals 0 here in this problem. And so at that point, determine the absolute minimum value. The absolute minimum value is going to be the negative 8. Okay, and it's going to occur at the left endpoint. Okay. So with that said, they basically did the same thing we did here. They're just using the candidate test to do that. Okay, and the absolute minimum value is negative 8. So point breakdown. They gave you a point for considering 0 and 6. Okay, the only two that would really be viable minimums here because of where the derivative changes. Okay, and then determining the negative 8 is in fact the lowest, and then your justification again is your candidate test. Okay, and part C says on what open intervals of 0 to 8 is the graph of f both concave down and increasing. Okay, so keep in mind that if f is concave down and increasing, so remember this is about f. If it's concave down, that means f double prime would have to be less than 0. Okay, and if it's increasing, that means f prime would have to be greater than 0. True? So we're looking at a picture of f prime. It's greater than 0 on 0 to 4, and then also from 6 to 7 or 6 to 8. True? Okay, the other issue then is where is the second derivative negative? In other words, where is f prime decreasing? So we want to know, okay, this translates to f prime decreasing. So where is this picture that we're looking at? Where is it both positive and decreasing? Well, clearly from 0 to 1 it's positive and decreasing. From 3 to 4 it's positive and decreasing. And that's it, isn't it? So we would say from 0 to 1 and from 3 to 4 because that's where f prime is positive and decreasing. And those are the two stipulations we're after. So if you gave the answer correctly at the two intervals, right, and then you gave an explanation that's correct, you got another point. Okay. All right. Then on the last part, says on part D that this function g is defined as f of x all cubed. So g function here is fx all cubed. We know f of 3 is negative 5 halves. And it says find the slope of the tangent line to the graph of g at x equals 3. Well, as soon as I see that, I'm going to go ahead and do what I always do, which is write down the point slope form first, because we're looking for an equation for a tangent line. We're given the x value here, so that's 1 out of 3 things that we're given that we know. Good. And then we need g of 3. So if I need g of 3, I'm going to be putting that into the g function, which means I'm going to put it into the f function, and then cube it. Now f at 3, okay, from our previous work, where are we at here? We don't need that. The g, it's right here in front of me, sorry. So that f of 3 is negative 5 halves, so it's going to be negative 5 halves all cubed. So that would be 125 over 4. Okay. And then finally, we need the g prime to figure out what the derivative is at that point to give us our slope. So we got to recognize that it's a chain rule problem. We'd have 3 times f of x to the second times f prime. And we want to know that at 3, so we go f of 3 times f prime at 3. And when we do the math on that, f at 3 we know is negative 5 halves. F prime at 3 is from the graph. That's 4. Okay. So if we do the math on that, we're going to get 25 over 4. Times 3 would be 75 over 4. Times 4 would be, of course, 75. So our slope here would be 75. And so our final answer then would be that for the equation for the tangent line. Actually, they just wanted the slope only, so we really didn't need to write the equation, sorry. So finding the slope, we get 75. They gave 2 points for 3 points for that. If you found the derivative of g, they gave you a point. So in other words, if you recognize that it's a chain rule problem, okay, found the derivative correctly, you got 2 points for that. And then if you plug the 3 in there and got 75 for your slope, then you got the other point. Okay, questions on anything on number 4?